Okay, hi everybody. Welcome to today's lecture. Today the topic is services and service architectures with Java. And I will, before going through the general lecture slides, I will, as I did last time, have some pointers here that relate to what's happening outside of the course. News, and also what's happening inside the course, meaning course participation and your progress. When it comes to the internals of the course, then I'd really like to compliment three of you who have shared the repository and have been pulling all-nighters the weekend, as I saw it, in order for you to finish the first assignment. And I think this is the road to success for the course, to really try to hit the deadlines. And tomorrow I will have some time to give you feedback on what you've been doing, and so you can be expecting some comments in the issue tracker on the repository that you put up online. And I would really encourage you, everybody in the course, to take advantage of this opportunity. I think it was probably an interesting learning experience for the three of you to collaborate in that way. And you might have collaborated very closely by communicating directly with one another. That might not be necessary. You can even be working completely detached, just contributing different parts of the software. As long as you make that transparent to the others that you're working with something, then you can really help each other making progress. And you learn a lot about how others code and how you can potentially improve your software. So some comments ahead tomorrow. I'll also put up some references for that actually push forward the pedagogical advantages of collaboration in through actually working together. And that said, another aspect that I'd like to raise is the little activity in the forum when it comes to the more theoretical aspects, when it comes to the patterns and what really is important for you for the examination is that you are able to explain the different patterns and how you were able to use them practically. And for that, you will need both practical and theoretical experience. So take this with you if you have any questions or things that you wonder about the questions that are put up in the learning objects that you should be answering, and you're not quite sure about the answers, or you just want to ponder about things that might be nonsensical to you, then please raise them. We can have discussions about them. Yes, that were the first points. Then an interesting happening on Friday. Oracle announced that the Java EE process and all standard and specification work are going to be outsourced to become open source and be taken care of by the Eclipse Foundation. And that is noteworthy because the Eclipse Foundation is known to be very stringent when it comes to the publication of new versions of software. And their maybe most known product is the Eclipse IDE. And those of you who have used Eclipse know that they are very good at sticking to deadlines and actually making the feature requests work. And they have a very transparent process of telling you what's supposed to be in place at the new release and whatnot. And you can actually really take action and participate through the forums without having any legit background or knowing anybody there. So you can just make your voice heard, which is great. So they call this project EE4J. and I'm not quite aware of when this will actually take action, but it's a positive movement because we've been waiting for the release of the 8th version of the Java EE standard or specification since at least some years now, and the last version was in 2013. So it's expected later this year, and if things really take off the way that it's projected here by experts, then we can expect new EE versions coming up every year with improvements, especially with respect to cloud. And that's really what's required to simplify software development for Java developers in the future. So this is very positive. Yes, so good. Let's get started with the, I see there are no questions here. Let's get started with the lecture material. Today I'll try to share the correct slides so that you can be with me, and I hope that today's lecture will not take extra much time. I think we'll actually hit it this time to be about 40 minutes, then a 10 minutes break, and then about 40 more minutes or so at max. It's a bit lighter lecture this time. Okay, so let me share the screen. There we go. The material that I will go through is based on the content on this slide, and especially most significantly the chapters in the course book and the Java EE tutorial. But especially for those of you who will be actively working on the assignment, which I hope all of you do, you should also take a look at how one of the service architectures, the traditional service architectures that's been created, that is native Java, remote method invocation works. And for that, there is an introduction link here in the tutorial. On top of that, there is a more modern version of remote method invocation. I call it more modern because it's internally based on HTTP2, and it is created in order to be very efficient. It's called gRCP. Actually, it's called gRPC, not RCP. This is a typo. It's a remote procedure call, and you can use that link here to get to the place where you can find out more about it. And it's actually an open source project that's been created and started by Google, and that's received a lot of traction and interest in the different service communities. People that were using REST services and they want to go ahead with more efficient solutions, they often turn to gRPC. But more about that later. So an overview. First, we'll talk a bit about distributed applications. Also give you a brief historical outlook on how distributed applications have looked through the past 20 years in Java. We'll then take up the three main patterns that are of relevance with respect to this chapter. So if you are well versed with these three patterns, if you know how to use them, if you're able to explain them, then you shouldn't have any problem of first applying them in the assignment, and then second, giving me a good impression in the oral exam. Then we'll take a look at one specific service-oriented architecture or service architecture, the remote method invocation. And then we'll take a look at other service architectures that are based on what's mostly used these days, and that is REST-based web services, but also a bit of looking back into how SOAP-based web services actually work in principle. So if we just take a look historically at some important landmarks, and this is by no means exhaustive. It's rather a way for me to try to give you an idea of how we actually ended up here in the lower right corner with EE4J as it's called, the project that should substitute the Java EE, or that should lead the Java EE progress for the future. During the 1990s, a number of different distribution technologies for client-server communication have been created. Some of them more low-level and more simplistic, like RMI. RMI does not have, like, it stands for Remote Method Invocation, as I already introduced earlier. It doesn't have the ambition to be used for distributed systems per se. It's mostly a way for you to have to easily create client-server applications where you can shift not only data but even workload from one node to another, or to a number of other nodes. Today we're using completely different systems to do these kind of moving of code. For instance, using Apache Spark to have more advanced communication movements, but RMI can still be used fine if you just want to connect a client to a server and have a simple communication going on between them in some proprietary format. During the 90s, there was another project called Genie, which was pretty. The objective with Genie was very different, and it's much closer to what we today talk about when we talk about the Internet of Things. The ambition was to have completely detached applications that in a completely distributed manner could communicate and exchange messages and even exchange code. And that supposedly even in a safe way, so that will be able for us to hot deploy applications, to update software in systems that we at the creation time even didn't know would exist in some years ahead. Fortunately, the system was not really adapted, and that's probably also because it was very complex to get things working at all. So it turned over to become an Apache project, Apache Riva, and I don't think it received any more traction. Sometime during the 2000s, the Apache Riva project took over, but these days I don't think anybody talks about Apache Riva anymore. Now, Corba had some of the similar issues. All the big corporations that were putting money on building systems with the platform-independent new language Java were gathering up and coming up with what they believed would be smart abstractions for interfaces. And we've seen this in history before. If we look at the internet stack and we look at the ISO OSI model, then it becomes obvious to us that sometimes we plan ahead things and they just don't turn out the way that we plan. So the ISO OSI model never got adapted. We have the internet model, which is much more simplistic with the TCP and IP stack. And the same happened with Corba. Corba was much too complex for people to use in practice, had far too many layers and too high learning curve, so it never really received enough traction. Then still people knew and realized that we have to get better at separating our components. The object-oriented movement contributed a lot to that. So people started talking about services, especially when we talk about distributed systems where you had components and multiple computers that were far away from one another. We don't only talk about components, we talk about services that interact with one another. And they should be reusable because it makes sense for us to be able to reuse the same components at different places. We don't want to maintain the same code in multiple places at the same time, etc. And so among other bodies, the OSGI Alliance formed, which is a number of automobile and other banking industry partners that wanted to have a very flexible platform for Java that would allow us to be able to hot deploy applications and to have this component based system that where you can easily plug in software at runtime, and have an abstraction that allows this not only within your computer, that you have a local distributed application that just has components that plug in and plug nicely during runtime, like Eclipse. Not only that, you should also be able to have this on a larger scale for whole network clusters where these services will work nicely with one another. So that was the ambition forming in 1999, and based on that, the Eclipse project was built, which is one of the first and most renowned implementations of the OSGI specification, which is completely based on Java, the component-based system structure. And at the same time, people were, or a bit later, people were involved in getting the abstractions right and better in J2EE with an improvement of Corba, which they termed Enterprise Java Beans. And there were improvements in version 1 and 2 that took all the knowledge from the bad practices and the bad experiences from Corba to the next stage and tried to improve them. And they made some progress, but unfortunately they didn't really get to the point where developers felt comfortable using Enterprise Java Beans at that stage, because it still was very clunky to create the remote and local interfaces and differentiate between applications that run locally and remotely. And that led to things getting better and more robust in Java EE version 5. And that was announced in 2006 with EJB 3 standard. And approximately at the same time, a work written by Roy Fielding received a lot of traction, who was writing a dissertation in the year 2000 about the REST approach, the REST architecture of how we can actually use resource-oriented thinking in order to abstract our services. And I would say since the year 2005, this received more and more attention. And we know today that it completely surpassed SOAP and all other web-based approaches that were using HTTP as a protocol in order to allow bridging systems that were not only in the same platform, but platform independent. So HTTP was the natural choice, and REST showed to be much more efficient and simple in its working procedure compared to SOAP. This all led then to, in the recent years, a better understanding of how SOA, the service-oriented thinking, should be implemented. And many people talk about microservices these days. And there are people that actually say that, and experts that say that microservices as SOA done right. So the approach of the idea with SOA was correct. It was just that the implementation was complicated because we didn't get the abstractions right. With microservices and the development of containerization and the DevOps movement, we actually get things more correct these days. We have better possibilities to really abstract our services easily and on the right level of abstraction and the right level of granularity. So we received the opportunity to create microservices, services that could live in containers that are independent from one another and that could easily communicate via standard interfaces with one another. And based on that, in starting 2015, about the development of so-called embedded application servers came to life. The idea there being that before, application servers have been always very clunky to create. It's an environment that is very complex because it allows many applications to live co-located, and that could create a lot of difficulties, and it requires a lot of synchronization between the processes, and it requires a lot of configuration. And for the developer, it requires sticking to contracts, many things have to be learned in order for you to do the right thing. And so using the concept of microservices and having small abstracted services, we might not need to have multiple applications running in the same server. Why couldn't we just create a jar file, a big jar file that contains everything that we need, and have that be deployed as a container? And that's what happened from then on, in a movement that was parallel to the Java Enterprise development, because as I mentioned earlier, in 2013, the development of Java EE has somewhat halted for a while. So there were some people that in the community that created what is called the microprofile, and in the microprofile they came up with ideas of how the different vendors could create abstractions that are meaningful to everybody, so that people can, that developers can reuse the same applications easily using similar interfaces. So now these days we're using fat jars. We can, just by running a Java jar and given our server jar file, we can run complete application server applications, as we do in the course, as you will see later in the course. This is how this can be done, and it's easily testable, easily deployable, easily updatable, and has many advantages. And significantly, it reduces the number of packages that you have to have in your server. So you don't always have to go with the full-fledged application server. Then another important thing that happened, given the microservices, was that now that we have all the communication going through HTTP, and with the rising understanding of security issues and the move to HTTPS as a requirement for almost everything, people at Google came to think of, well, we should have a more efficient way of communicating our data. And JSON was more efficient than XML, definitely. But there are many more hooks that could help us making things even more efficient and also more feature-rich than the standard REST approach, which, I mean, is also quite, if we look back now, we have 2017, it's 17 years old in that respect. So something could be improved. And now, knowing that HTTP 2 is on the way, and the specification has been final for some time, they've been starting to create a new version of a remote procedure call mechanism that is based on HTTP 2, but which is more efficient in communication due to many respects. And I don't go into detail here, but to those of you who are interested in that, you can deep dive into that and get back with discussions. I think this is pretty interesting stuff. Our gRPC, it allows us also to abstract away. For instance, we don't have to actively use WebSockets in a different way as we use simple synchronous REST services or asynchronous REST services. So we do streaming in the same way, or almost the same way as we do simple REST API calls. So it simplifies for the developer. Once you understand how things work, you don't have to go with two different ways of approaching the data communication using WebSockets and using REST. You can just go ahead and use gRPC and do that all the same way. So yeah, there we end up now today, or at least on Friday, the news came out. EE4J is being formed, and there's going to be a lot of changes in the near future. And I think positive changes, especially because cloud development has changed the way that we develop entirely the last 5 years, if not the last 3 years or 2. So this has really changed the way we developers have to think when we create our applications, and this will help us in Java to simplify things that not everybody has to think and know about all the details in the cloud. But we get the support that we need for the future. And now, talking about service architectures, I would just like to give you an outline of what is so special with that. What does it mean to be a service-oriented architecture? So in principle, it's implementing the design pattern service orientation, which is not part of the course in that sense. So just for your reference. And all functionality that is being delivered is delivered through services. We usually talk of consumers versus providers. So we have a provider that is offering a certain service, that service is registered in some kind of registry. It's could be called something else, but this is the most abstract and general name. It's the registry, and given that, a consumer can actually look up the services that a registry offers. It can request a certain service, and the registry helps them by a resolve to actually resolve where that service can be consumed. So the consumer then goes to the place, and in this scenario, it's usually that we're forwarding IPs and ports. So there's a certain service that is requested. The registry can tell the consumer, well, these are the number of alternatives, and the consumer then can make a qualified decision of where to go in the consumption stage. So that's basically the whole abstraction. So what you receive is you have a very loose coupling, because you could potentially change the services meanwhile running, or you could add multiple service providers, so that the consumer has a richer choice. And the examples of these service-oriented architectures is OSGI. The Equinox implementation is which Eclipse is based on, is a completely service-oriented architecture. So under the hood, it's a pretty neat software. So the design is really nice, I must say. But OSGI itself has its flaws when it comes to versioning, for instance. So it's not perfect. And those of you who used Eclipse extensively are quite known to the fact that it could just crash, or plugins wouldn't install, and plugins don't like each other. That is because of some versioning issues that OSGI by itself can't fix. And that's why we are looking forward to the new project in Java 9, which is called Jigsaw. That's just a side note. And another service-oriented architecture, if you so wish, is the Docker infrastructure. So you also have a registry where you can register all your containers, and you can download the containers from that registry and run them locally, or put them to platforms such as Kubernetes in order to execute them in container engines without worrying about computational entities, without worrying about computers. You just abstract away that layer. You just have a cluster of machines, and you don't really worry. You just want things to work, and you set up metrics that make sure that your system works the way it should. And here again, without trying to going too far here and repeating myself too much, another alternative name is oftentimes a broker. Could talk about the service registry or broker. And two examples that are taken up here: SOAP, which you probably not be working with anymore, and it's the SOAP broker was called UDDI. And as another alternative, we have the plugin and feature structure of Eclipse Equinox here, where the service registry was simply called the service registry, and we would define our services through XML files to this registry. And then the other services, for instance, if you created a plugin, you could ensure that, or you could require from Eclipse that certain other packets are installed or available in order for your system, for your service to work. Otherwise, they would refuse to start, and that would be it would be easier for a user to debug the difficulties if this were done right. So let's see. Okay, so that's a bit of explanation of why we're here, and what we're why distributed systems or service architectures are important for us when we work with information systems and enterprise systems, because these days they are highly distributed, and we have multiple ways of or strategies of distributing our components. And let's just, for the sake of it, consider the situation where we have a client that is physically detached from two components that are that it requires, and that are both working with one another. So the houses here, they model the physical detachment, and of course, then as a distribution strategy, this might not seem too tempting, because if these components really work a lot with one another, the processes are slow. Because we have to consider all the latency that is going between all the calls. And sometimes we have this imperfect situation where we just can't change this. You know this from our systems here in Sweden. We have certain laws that we have to apply to. Certain data has to be in place in certain places, and some data centers don't offer certain features. So we might end up in a situation where we have to live with this. But if we can, sometimes we can, often we can. We should try to have these components be placed in the same physical location, and usually then the client still is somewhere else. And this is the common situation where we have a simple client-server situation with all the components being co-located, being able to communicate fast with one another. No rocket science here, because the inside JVM calls are obviously much faster. Then, in order for us to be able to cover more workload, to be able to supply work for more than one client, or more than 100 clients, or 1,000 clients, or whatever our borderline is, we could do something that's called co-location. If we do things smartly in our components. So in a way, we would have to make sure that our services just can be replicated. And this is not always easy, because we usually have statefulness, we have databases, we have data dependencies in our components, and we have session data. So we have to make sure that once you connect a client to a certain component, that it really sticks to that component and not move to a component that is physically somewhere else and that session data gets lost. But luckily, the technology we're using today with systems like Nginx that help us scaling out simplifies these things a lot. So we don't have to think in terms of these session stickiness anymore. This is usually solved for us. But still, on the level of the application, we have to make sure that database access is still transactional. That said, that component one is not updating here on the left, is not updating something that's at the same time being altered or read by component one on the right-hand side. So these systems have to have some kind of sync, and that's why we're talking about transactional communication quite a lot later in the course. But this co-location is something that you will see a lot, and usually what we talk about is scaling out instead of scaling up. So you can always, when you reach a certain boundary of what you can actually cover with your computational sources, you can just add more computational sources. But sometimes that's not enough, or that's not the most efficient thing, because it might be expensive. So if you build your software smartly in a way so that you have that you can co-locate your components, that you have stateless components, then you usually get it much cheaper, because you can use more simple hardware, and you can cover as many or even more clients while being more scalable, because then you can just add another layer and another layer and another layer. And that's actually how systems like Netflix or Amazon cover all their customer base. So, but what if we can't separate? So we just cover the case where we actually can, but what if we can't? Well, there are structural ways of approaching this, because we know it won't be perfect, we will have a latency, but let us then at least think in terms of coarse-grained versus fine-grained interfaces. What does that mean? The objective is, for us, if we have components being placed in the the general objective is, of course, to maximize local interfaces. But the whole challenge now is, what if we can't? We have remote interface. Okay, so we have to accept them. But let us then think in terms of how we actually move our data and what data we move. And so one technique would be to, as we often see in REST interfaces. I don't know if you're using APIs, but if you, for instance, look at the Bitbucket API, it has a lot of data that it's sending to you if you request something, and of course much of that is relevant for you, but not in all contexts all of that is relevant to you. So you can try to tailor the remote interfaces by having coarse-grained calls. That means that a coarse-grained interface is an interface that has very specific calls for a certain need or requirement, and in that call, exactly that data is packaged that you would need. And it's coarse-grained, meaning that you have specific calls because you want to make as few calls as possible. Whereas if you look at the local interfaces, you want to have fine-grained interfaces. For an easy structure, you want to make things easy to understand, have getters and setters for things with not too many parameters, etc. And also because it's easier to read, but also it's as efficient. So for the JVM, it doesn't really matter. It will anyway change the code in a way that you wouldn't expect it probably. So internally, it might create some coarse-grained interfaces anyway, but that is not important for you because you want things to be understood by others and yourself tomorrow. So that's why we look at fine-grained local interfaces and coarse-grained remote interfaces, reducing the calls as much as possible. So in general, then there is this what Martin Fowler calls the law of this. The first law of distributed object design is that you just don't distribute the object, because once you distribute them, there are a lot of effects that can hit you that you wouldn't directly expect, like how do you sync your data locally and remotely, and what of the data is really expected on the client side. Do you want all data to be shared? So you have to make the contract even more explicit of what data actually is fresh in your objects that you're sending, and what data should be updated maybe when responding back with objects. So the contract becomes very complex. So the easiest way to get around this is just to not distribute the objects and have simple interfaces that make clear what data is sent and what the purpose of that data is. And so we can go back to the original natural separation of systems in our applications with the front end, the middle tier, and the back end. And we've talked about that, and we will get even deeper into that during the next lecture, learning objects. And what I'd just like to highlight here is that we can do two things, and I mentioned that already earlier, but it's an important point for you to really grasp. That is, we can have two scaling strategies if things just don't perform enough. We can scale out and we can scale up. And scaling up usually means that you buy a bigger house. In this example, at least, you would use more CPUs, or you would use more memory, or whatever resources are required for you to serve more customers. Whereas, and that's also called the vertical scalability. And then we have the scaling out, which is also called the horizontal scalability. And that's what I earlier showed you with the co-location, where you simply replicate your stack, and by that allow better throughput or latency, or whatever your metric is. And some of the nice things of this is that if we have a distributed system where we have our front end, middle tier, and back end in different places, we could actually do both of this, the scaling up and scaling out on all layers. So it's important for us to measure actually where the deficit and the problem is. Where is our bottleneck? Once we find that out, we can choose our strategy. But the most important thing is that we first measure where the bottleneck is. So we come in to the three distribution patterns. And with that, I will finish the first part of the lecture. It's three patterns. They're closely related, actually. And I want you to think a bit about them. And when you develop them, really challenge yourself to see the differences between them, because they might not be obvious in the first place. The first one's called data transfer object, often shortened with the acronym DTO. It is an object that carries data between the processes, and its objective is to reduce the number of method calls. And you might recall my dialogue there, or monologue, about the remote interfaces that should be coarse-grained. And here we really see how reducing the number of method calls fits nicely into the objective that we have in remote calls. But how is that done? So here's a practical example of that, which is very simplistic, but I think you get the point. Here to the right, we have a model of albums and artists, and an artist can have multiple albums. What we would do in a local system, we potentially would call from one component to the other. First, we would call an artist, and then given that artist, we would make another call to get the albums. But since we have all the latency overhead over the wire, we want to make sure that this is assembled to one data set. And that is why we use the album assembler here, in order to create something that we could call the album DTO. And DTO is a known term, so people are very familiar with it and know actually what it means. Once they see that, they see, aha, okay, you try to improve performance by combining data in a meaningful way just for this application. You tailor your data to the specific application. And that's basically it. So what you send is the DTO. You send it from the server to the client, or from the client to the server, depending on your model. And what you do there is that you just untangle it. So you can use it either way. Either you just use it directly in your data, or you have a similar data model as the one presented here to the right, and then you just, based on that, create your objects, your artists, and your albums based on that. So this is a way for us to reduce the number of method calls, and that fits in nicely to our objective of reducing latency. So that's data transfer object. We have some advantages, disadvantages, as usually, as you will see here, and as you've already seen in the first lecture probably, that one of the common disadvantages with most patterns is that you add another abstraction layer. But the idea with this is that people who see this abstraction layer are familiar with it. And since they are familiar with it, they can easily understand and interact with the code in an easier way. So the additional layer should add value here. It's not necessarily a disadvantage. And the same counts for advantages here. We have an advantage that is there is no shared behavior. And that could sound like a disadvantage, because behavior in the sense of objects is that we could execute code. We can send code over the wire. And with DTO, we can do that because that's not our objective, right? We want to simplify and to minimize the communication overhead. So we usually don't share behavior, but that's not our objective either. So it reduces the bandwidth, and also the caller, and that is what I would like to summarize with the third point here with the getters and setters. The caller, the client, for instance, if a server sends a DTO to a client, knows exactly what it can expect from the object. Whereas if you send objects from the server to the client, it might be that certain getters or setters don't work because they might just not be active for this feature or this client because of reasons of security or whatnot. So it's much more straightforward and easy for the client to interpret. And also it doesn't pollute the server-side domain model with getters and setters for data that are actually not otherwise required locally. It increases the code complexity because obviously if you have to create DTOs for each specific customer or client, then this increases your code base, and it requires you to maintain all that code, test all that code. But of course, then with the advantage that you can really tailor your application for each and every client depending on the client needs. And only same platform is also only partially true, If you do it the simple way with a serialization in Java, then you can only use the same platform. But today we use JSON broadly when we send data via REST, and we can use the DTO pattern through JSON the very same way, just simplifying and minimize the data that we want to send, and untangle it or unmarshal it on the other end. Yes, and by that, by definition, it's tailored to the client and the UI, which can be seen as an advantage and disadvantage. So that was the first pattern. Second pattern is called remote interface. Excuse me, remote facade. And a remote facade is a coarse-grained facade on fine-grained objects. So it's abstracting something. It's trying to translate something from one end to another end. And it does that to improve efficiency. So as you already see, all these patterns are about efficiency. We want to improve performance over a network. If you just the example here, you have an address class with all the different getters and setters. And if you were to send a HTTP request for each of these getters, there is a lot of extremely much overhead that is just unnecessary, and all the latency. On top of that, you would obviously just want to get all the address data, and that's what the facade is doing. It's summarizing all these fields, and at the same time, it can do that for as a collection of different objects. So in this case, it's very simplified. It's just the address facade, but it could be the facade that is supplying address-related data. And in that facade, you could send users with certain address, in certain address areas, or you could send address information for specific users. And you can really tailor this to have a facade that just fulfills the requests that you usually have for your client, and using that in a coarse-grained way. And this actually this produces an API. Usually, we use the remote facade pattern in order to extract our APIs, and it works well with DTO because you can actually send these data objects, the DTOs. You can have an internal translation in the facade that is marshalling and unmarshalling. That said, I guess for it's serializing and unserializing the data in the address facade, so that this work is completely done in the facade, and structured in the facade for your purpose. So it plays nicely with the DTO pattern. And then just generically, and I think I pulled this one in the introduction slides too, the gateway pattern, which is a data access object pattern, which is taken up in the pattern in the book, in the course book in chapter 7. This is why I repeat it here. It encapsulates access to an external system or resource. And we touch upon this when it comes to databases. We have a DAO, as it's called, the data access object, that is abstracting us from the persistence layer. And you can discuss in the forum and on Riva, or here maybe on the message board, what actually is the DAO that we're using to persistence in the learning object 1. And then we have gateways that abstract to external systems, like a client-server relationship. And there you would naturally include the remote facade as an instance of a gateway. So data access object is an instance of a gateway that is abstracting the resources, and usually remote facade is something that is abstracting external systems like services. And the advantage with this is that it hides a lot of complexity from us. We don't have to care about all the JDBC stuff when we do JPA, for instance. But it adds another layer, so we have to learn that layer and understand it. Okay, so let's take a break here. We'll be back 10 past. And if you have any questions or comments, just let me know, write them down here, so I'll address them in the beginning of the second half. Okay, so let's go on. And I'd like to start with a brief recap of the patterns and how we can combine them. What I think is most important with this, going back to the picture where we look at the center, the remote coarse-grained interface, and we've been learning about remote facade and DTO, the data transfer object. So in order to achieve a minimization of latency, we do have the remote interface being the API between the components here, and the DTOs being the data that is actually sent between the components. So you could consider in many situations when, for instance, for the Bitbucket API or Dropbox or whatnot, you usually use JSON data, and in a way this is usually being represented by some kind of DTO, not really optimized DTO, but you could potentially optimize that to suit certain client-specific needs. So just to get that out. And we can focus on what the different kinds of services that we can, how we can conceptually differentiate between services. So we have a provider and we have a consumer of the service. We learned that, and we learned that usually the services are looked up by some kind of registry mechanism. But eventually then the communication has to take place. The question is, how could one communication differ from one another, and how can that impact the performance or expected experience for the user? And we differentiate between two dimensions here. We could even go further, but just to start with, we have these two dimensions, which is the type of communication in terms of calling semantics, which is either synchronous or asynchronous. And we have the transmittal, what's actually sent, the data or behavior. Are we sending data or are we sending behavior, which usually is equivalent to code or objects that actually encapsulate code. So whereas in the communication property here, we can only choose one of each. Either it's synchronous or asynchronous. In the transmittals, we can choose either to send data or to send behavior, or we can choose to do both. And in order for you to get an understanding, we deep dive. So here we have an outline of what the differentiation between synchronous and asynchronous is, and this might be something that you're familiar with. In that case, this makes your life here much easier because you already know what I'm going to talk about. But what it basically means is that the difference between waiting for a response or not waiting for a response. And in the case of the applications that we're usually using HTTPS to communicate, and there we're making synchronous calls to services, means that we actually want something back now. And a good example of that is a browser. So if you're browsing to the news page, you're actually expecting something to come up soon so that you're able to consume that information. Whereas if you are sending a mail, you're sending something not expecting a response immediately. So you can go ahead to something else. There are advantages and disadvantages to both models, and it depends on what you actually want to achieve for your clients. Usually the asynchronous model is much more scalable. You have a more loose coupling between the entities, and you can process many more commands at the same time on the server side or on the receiving side, the service provider side, say. Whereas in the synchronous case, you usually have some kind of stickiness to your data, which oftentimes also requires some session information to be stored, and that will require you to have a cache for all kinds of communication on the server side or the provider side. So synchronous communication is these days said to be tried to be reduced on the server side if possible. So that's why many of these asynchronous frameworks pop up that solve things reactively. I don't know if you've heard about the term reactive, but it comes up a lot, and there are web development tools like the React tool, JavaScript, that simplifies this development. And there are tools also for Java, etc., all other development environments. And here, just to show this, in these two examples here, on the left-hand side, we have a typical synchronous communication in green, where we're sending a request and we're waiting for the response. And that waiting could take a lot of time. Here, actually, in this case, I didn't really go so far to make this more obvious, so that you actually see that you have to wait a long time before you get a response, but you're actively waiting. Whereas on the right-hand side, you could commit 3 requests, and they might be even related to one another, and then you get a response sometime later. And that might not be what your customer or your client is wanting. Maybe they want a quick response or feedback, and that can oftentimes be handled with some kind of human interaction thinking, like progress bars or partial information, where you, for instance, in web browsers, you first send text so that users can read first, and then later pictures, and the very last videos, so that the user can start interacting. But this is more diverging from what we actually want to communicate here. We just want to say that, well, you can communicate synchronously or asynchronously, and we have the tools in Java EE that to do this very simplistic. The basic model is synchronous because we're using HTTP. So if you want to diverge from that, you have to do this explicitly in the code, and we will learn more about that in the next learning objects. And yeah, most of what we're doing in the course is synchronous application, because that is the default, so to speak. And then we have the differentiation between data and behavior. And here, one of the examples that I can give you which really differentiates this is JSON is usually not containing any code. You don't want any behavior to be moved from one JSON to another, because then it could be injected, and you could be falling victim to cross-site scripting or other mad things. So we usually don't want that in that sphere. So we're only sending data, no behavior. But when we so that is the web service sphere. But if we then compare that to remote method invocation, where we're actually sending objects, and we even send objects that have executable code on the calling side. So the consumer actually, without knowing exactly what the code is, trusting a certain provider, is executing that in its own virtual machine. That is behavior that we're moving. That's when we're talking about behavior. So RMI is actually moving both data and behavior. So you're moving the fields, and you're moving the different methods that can move. And that's very powerful, but it also comes with the price of the requirement of a good trust model. And yeah, so that is a clear differentiation between the two approaches, between web services and RMI, the behavior as part of remote method invocation. And here we see a conceptual map of how remote method invocation works. It is a clearly synchronous communication. We cannot even make it asynchronous in a non-trivial way. It's not built for that objective. You can locate the objects through a registry, so it's a service-oriented architecture. Because you look them up through this registry. It's a service that's running by itself, and it's running on a certain port, which is commonly known to all the stakeholders. I think the default is 1099 or something, so that everyone knows, okay, there is a registry running on that server, so we go to that port and request the services. We do a lookup, as it's called, and then what's been done is it's actually using HTTP in order to move code, so the server can place its code in through on a web server, which is put up, or which you put up, and which you tell the registry. So the registry knows where that web server is. And this is all simplified in RMI, so you don't have to actually create your own web server. So then when the client is calling the registry for a service using a lookup, it receives information about both the service and the web server, where it can download the code. And of course, now we know the internet is open to everybody, and so we really have to make sure that security is in place here, because if some man in the middle here is hijacking information and moving code to the client without any trust verification, then the dynamic class loading can easily lead to some malicious activities on the client side. Anyway, this is the structure, how it works. The code is moved through a commonly known place, and that is usually a web server using HTTPS. And now let's have an outlook on web services. And my understanding of your progress in web services is that you haven't really touched upon them in the education, and I don't really have the extensive time here in the course to have a deep dive on web services. What I will do is just give an outline on how they conceptually work, and we will later implement them, and you will get a feel for it. I don't think it is conceptually so difficult, and if you have any questions, just shoot. But for this course, this has to be enough to know that it's communication via HTTPS, and it grew from the idea of remote procedure call, which is just a generalized view on how to make calls from one computer to another through a network. And what is advantageous with web services compared to just creating your own socket communication, for instance, is that it's following a standard, and or some standard at least. Here we have two opposing ways of doing it with SOAP here, JAX WS, which were the original web services here on the left, and on the right we have JAX RS, which are the what we usually now refer to as web services, the RESTful web services. And the advantage then is that it's not proprietary. It's easier for others to learn about this, and it's easier to find tooling that supports the use. And the traditional protocol then for the web services has been SOAP, heavily based on XML. And that has been powerful in expressing things, but it's been also very clunky. And these days we usually use RESTful services. I'll go a bit into what that actually means, but basically it means that we are communicating through the primitives of HTTP, which are the put, the get, the push, and the delete. And we don't need XML. We don't need any service description. It's more loose. The definition of the data is more loose, and we can skip XML. We can use JSON, for instance, which is more efficient in terms of bandwidth. So there is no explicit contract in RESTful web services compared to the original SOAP web services that always required a registry with a complex lookup. This is not required for RESTful services. Yes, and so I think one of the important points here is that in this summary, if you look here to the at the right at the cases where you use REST instead of SOAP, is that the second point here, bandwidth is important. So if bandwidth is important, then we use REST. And these days, even tooling is much more advanced. Security has been phenomenally more improved during the last 3-4 years in RESTful services. We can test it much more simply. There are so many advantages. So the general recommendation is to use, in a world where you only can choose between SOAP and REST, then you choose REST to start with, because of all this is what the world has chosen, simply. And so if we have our enterprise environment here to the right, where we create our internal services, we can obviously connect external services through the internet using SOAP and REST, if these are two of the alternatives. And we prefer REST for all kinds of services, complex services, security, scalability, everything is covered these days using REST. 5 years ago, I was still talking about SOAP as being the preferred way of doing things, because the tooling was existent and it was considered to be more secure. But today, this is not true anymore. And also, if we consider all the services that we have internally, because we might have supportive services that are not exposed to the internet, we usually also use REST in there, because REST is pretty efficient. And as I will explain a bit later, another alternative which might be even more tempting to use if you have a bit of extra time and you have a bit of extra stress on the performance side of things, and you want to do streaming, etc., more advanced stuff, then you might be inclined to use gRPC. And so there are obviously, if you have this, if you have a service structure, service structure, you have clients, you have a service, then you require different APIs, one to define the services and one to consume them. And that is both abstracted in Java, in the JAX-WS packages on for the SOAP, and in the so that's the SOAP way of abstracting things here. JavaX.jws web service, and all the annotations that are included in there help you to externalize your services. So if you have a service that you could easily call from within your application, an object that you instantiate, and then you call a method, you could basically, in many cases, if you're if the data that you're sending back and forth is serializable, basically, then you can make it become a web service. And the annotations here help you doing that without adding any code. So you do, again, configuration over coding. And here is an example of that. So you have a simple Pojo, simple bean, and it's a hello bean. And what it does is just saying hi to the whatever person connecting. And just by annotating the class as web service here and the method as web method, you basically create the service. You don't have to do much more than that. And based on that, it's creating a WSDL file that can be exposed, and that is automatically exposed by the application server, and that can then be called. Defines the contract and can be called by the client. And here is the client then on the other end. I crossed, where the crosses is the important part. You can simply by declaring a web service ref annotation and linking that to the correct server or the correct file, you can actually inject an instance of that service that allows you to, in this case, say hello. And so the call here, the main call here, is going to the hello world calls. And that is because the WSDL definition that is being referred to here, which might be a bit similar to what you've seen before in RMI, where you have a web server that is the known source of information. Here, the WSDL is the known source of information for the client. it has the information of where the server is, what the server port is, what port it's running on, all the information in order to invoke this automatically and for you to call it simply. And so basically what you do here, furthest down, you see that you inject given the service object that you're receiving, you get what they call a port here. And through that port, you make a remote request to the server. So, and all the complexity behind, you don't have to worry about. That's basically the whole idea of abstracting things here with annotations. And for JAX RS, for RESTful services, this is pretty similar. It's just simpler, right? So you don't have to worry about this WSDL files and how to find them. As long as you know how the service is formed, you can just call the service, and you can test it easily with command line tools, which I also will show you. And so one of the biggest differences that people talk about is that REST is not a service. It is not a service architecture. It's a way how to access and manipulate resources, and in that sense to manipulate state. And that's why it's called stands for representational state transfer, and that's why it also fits so nicely into the HTTP protocol, because the HTTP protocol has just exactly those primitives that REST is offering, and that is not by chance, of course. And it's made for the web, and it's made in order to be more performant and scalable than those technologies being come up before. And so the idea is, the main difference is that you don't call services, you just get or update or basically or delete or do all the CRUD operations on resources that you actually have access to. And of course, all the authorization, etc., we don't go through, but this is in principle what you're doing. You make changes to resources instead of calling services. But in principle, this can translate into the exact same thing as service-oriented architectures. So, and this is then completely decoupled from the representation of the data. What you're doing is you call things according to the API, and this we also talk about the explicit state transfer, meaning that REST doesn't suggest, the model itself doesn't suggest you on the server to store a lot of session information. It should be that all the information is sent back and forth between the state transfer. And that's also why it fits in so nicely into what I earlier explained about the co-location of components. If we have, if we don't have stateful components, if we have stateless components, it's much easier for us to replicate them and to have multiple of them running. And REST simplifies our thinking here. As long as you stick to the contract, it allows you to do really good scalable application design. And here is the counter example to what you've seen before for SOAP. What you define here is a path, given your application path on your deployed application on the application server, which is something that you will explore in more detail in the next learning object 3. You define where you can actually locate this specific resource. So it's not a service, it's a resource. That's important. And it also defines here the type of resource it is. So the method declares an annotation of type get, meaning that this is a get instance. We're not supposed to push any data or change any data. We're just getting information. And what it produces can also be specified. You can specify for it to produce XML, JSON, or plain text, or even binary files. This is up to you. In this case, it's just simple plain text. And so this is just the exact, very similar method compared to the web service that we've seen before, just that this automatically always sends out hello world. That is because it's simply a get. The resource, we're just asking for being presented with the current state of that resource. And so that was the server. And then on the client side, since this is HTTP, and since we're not requiring any nitty WSDL definition files that are complex, we can just open the browser. And if it's a get, then we just go ahead with the URL, and we get that data. So you could open the browser, and you will actually get a hello world there, if your application is deployed correctly. And so there are a large number. But that is only the get case. Obviously, if we use a browser, we usually don't use that for pushing data, and I don't even think the features are there to natively do pushing data, etc. We just want to consume information. Well, if you press buttons and so, then that's all implemented, obviously. But we don't want to do that when we're testing. But if we want to test a put or push, etc., then we can do that through numerous libraries. There is Jersey, OK, HTTP, Retrofit, and Retrofit is probably the most used and the most high-level library, which is very simple to use, also basically annotation driven. And if you want to have a very simple approach to testing these, you can use the curl, the curl command line tool that you can download even for Windows, I believe. In most Linux distributions, it's part of the most modern Linux distributions, and you can just run it, and then what you get back is the content of the page. And for web pages, that often doesn't make sense because that's HTML, it looks really cluttery. But if we look at the services that we've been defining here, then that could make sense. We just get as an output the system output of that data. So here we have just to give you an idea, a number of examples here. We could do a get by just writing curl and the address, the IP address or the address that it resolves to, the DNS, and a port. Or we could even leave the port because 80 is the default for HTTP and 443 is the default for the HTTPS. So that's a simple get, and what you get on the command line is then the page resolved. Alternatively, we could do post operations, just as another example. We can, of course, also do the other operations, but here the post is exemplified by some code that is placed on the page. So say we had a page here that has on the left a form that you can fill. You could either open the browser and fill that form by hand, or for testing purposes, you could just simply do a curl, and then in the data variable, you can enter the content that you're supposed to be entering, that you're interested in entering. And by doing that, you actually do a real post to the data, to the web interface. And also just another maybe interesting thing, if you want to serve or if you want to do any activities through curl anonymously, you can use the SOX5 interface. And if you have a Tor instance running in the background that's received enough noise in order for you to be safe, then you can just run on any kind of page, not only the Tor page here, a call, and it will be delegating this through the Tor network, and by that hiding your original IP that you're having running. So curl is a very nice tool. I can really recommend it for you. It's not perfect, but it's very simple to get started with. To sum up, we've been talking about service-oriented architectures and how they develop through the years or the centuries not centuries, whatever it's called, the last 20 years. And we've been looking into different ways of doing distributed computing, different ways of scaling systems, how we should place our components if we can choose, and if we can't, what we can do to counteract, and what patterns we can use to distribute things with good performance. And we've learned about some of the standards, the web service standards, and the Java-specific standard of RMI. And we've even mentioned gRPC, which is a new way of doing remote method invocation, just that it's platform independent. And now in the assignment, you implement a simple RMI server facade, which is actually an extension of the work that you've been doing in assignment 1. So it's invoking those domain classes. And based on that, you build an extra DTO layer in order to reduce data to specific calls, specific client-tailored calls that are reducing the workload to what exactly the client is required to see and allowed to see. And you're free to come up with an interface yourself in order to reduce this communication overhead. And if you have extra time on your hands, then feel free to experiment with gRPC. It's probably what people will use more and more in the next year, so it might be a good investment. But I'd suggest you not to do that now. I'd suggest you to do that maybe towards the end of the course if you have some time over, or even after the course, because the importance here is that you understand the concepts of distributed computing with Java, and gRPC then is just a detail, as much as a detail RMI is. And here is just a bit of an overview of how gRPC is different, because it thinks new. It allows, first it's fast because it's based on HTTP2, but not only that, those of you who have been working with JSON, you know that we have key value entries. And gRPC, by declaring an own protocol language, which is called Proto, requires you to write down in what order the entries are coming, and by that it is reducing the workload that is actually sent, because it doesn't have to send all the keys. So you define things actually through this Proto language. It's like an interface, a definition language, and that really reduces the overload. And well, otherwise it works very similar to RMI, but you see already here the difference when it comes to platforms, because we have Proto as the binding component in the center. We have exporting tools to all kind of platforms: C++, Android, Java, Ruby. So we don't have to stick to Java. We can communicate with gRPC to all platforms. And we can also do streaming using the same API, which is pretty nice because we reduce the extra work and heavy lifting with WebSockets. So that's to say about Learning Object 2. And now it's just for you to get back, knowing that I'll be tomorrow afternoon, Wednesday, and Friday afternoon. As usual, I'll be in the chat room. So if you have anything to discuss, something that you want to just ponder about the patterns or details about implementations, just go ahead. Yeah, with that said, I thank you for today. And yeah, we stay in touch. Bye.